Welcome back to the third part of motion control with an RC servo and an Arduino microcontroller. In part 1 we implemented a fixed sinusoidal motion. Card here, link in the description. And in part 2 we made the sinusoidal motion adjustable and also stop and startable at a defined position. So if I stop that now, we go to a resting position and I can start it again and it continues. I can, adjust the speed and I can also adjust the amplitude. All very nice. And for part 2, see that card and link in the description. However, I wanted to add 2 more features to the software. First, when you depower the Arduino and repower it again, it goes to a default motion state, which is really just this little uninteresting wiggle that we can, of course, speed up and adjust again in amplitude, but that's not very convenient. Would be nice if we could save a certain set of parameters for the motion, so amplitude and frequency, and that would be the start state each time we power it up. Second, we have measured for that servo what's the pulse width for its PWM signal to reach the middle position. And we also measured what's the maximum angle pulse width for the PWM signal to reach a certain angle up and down. But that's hard-coded. If you exchange the servo, you would have to recompile your code to get exactly the same range of motions again. That's also a little bit annoying. So these 2 problems I want to tackle in this video. And I have to admit, I already worked a little bit at the code. So let's have a look at that. So what are the changes I already did to the code? Well, first I included the Arduino EEPROM library. For you who don't know what an EEPROM is, most, not all, but most microcontrollers have 3 kinds of memory. You have the RAM, which is gone when the power is gone. You have the flash memory, where the program, your code is uploaded to when you're programming the microcontroller. But most, and all Arduinos, I think, have also an electrical, erasable, programmable ROM. And you could think of it like a little piece of flash memory, so it doesn't, its content survives without power, that you can write from within your code. And we will, of course, use that to store our parameters. Then I have defined further down here a struct, EEPROM data. That's basically all the data I want to store in the EEPROM of the Arduino. We start here with a magic number. More about that later, but basically that's our payload. The 4 parameters I want to store so they survive a power cycle. And we know that, know them all from the second part. So servo 0, middle position, servo stroke max, or plus minus delta of the position, the current servo stroke, what's our current amplitude of our movement, and the quadrant steps, which indirectly governs the speed or frequency of our motion. And I have here an additional constant, magic number. That's basically just a random number. And of course, that should be stored here at that position. How that works, further down. other changes of note, I declared the struct above, and I also have a global variable struct EEPROM data. The only other addition so far is that section here within the setup. So I do an EEPROM get at position 0 in the EEPROM. I think the EEPROM size in an Nano Every is only 265 bytes. And what that function does, it reads from the EEPROM our EEPROM data. Remember, that's basically 5 times 2 bytes, so 10 bytes in total. So starting with address 0 or position 0 in the EEPROM, it reads 10 bytes in our struct. So next, now comes the magic number. Next, I'm checking after we read our struct from the EEPROM if the EEPROM magic number is equal to our magic number constant. Meaning at one point we already written that struct to the EEPROM, and the EEPROM contains valid data. And in that case I set my variables, we already know them from part 2, with the content in the EEPROM. So I'm restoring all my parameters, for the speed, for the stroke, for the middle position, for the maximum stroke, from the stuff saved in the EEPROM. If the first 2 bytes in the EEPROM are not containing my magic number, then I fill my struct with my current variables, which have been already initialized here, and we had that constant further up, magic number, and then I use the EEPROM put to write the whole struct, the whole 10 bytes, to the EEPROM. The purpose of all that is, of course, if you have a new Arduino or a used Arduino that contains either no or some unknown data in the EEPROM, through the magic number we can check if it really contains the data we are interested in. And if that is the case, then we load that data. And if it's not the case, we write the data that is needed for our program to the EEPROM. So with that groundwork done, it was quite easy to implement or to solve our first problem, saving the frequency and the amplitude. So we know the problem. If I repower it now, it comes on with minimum frequency and minimum amplitude, and we can of course increase the frequency as much as we like and the amplitude to a state we are comfortable with. And now we can save it by pressing the push button in the amplitude rotary encoder. Okay, that should have saved exactly these settings, and if I cycle the power now, and switch on again, there we are. Perfect. And of course we can play that game a few times. So save that setting and we go into the off state so we don't have that jerk at the beginning. We repower our Arduino and we are at that state. Great. Let's have a look at the additions to the code. The changes to the code are really minimal. Just as a reminder, I am now also using that volatile Boolean stroke encoder switch, which is set in the background by an interrupt routine and toggles its value each time you click the button of the stroke encoder switch. How that is done, watch that video here about debouncing these encoders card link. Other changes only in the loop itself. Of course, I'm now using the stroke encoder switch red variable where I store the previously red value of the stroke encoder switch. And I initialize that variable here, stroke encoder switch red equals stroke encoder switch, as soon as I go into running mode. And if I'm running and if I'm not stopping, I just added here another if statement. So if stroke encoder switch is not equal the previous red state of the switch, then I set in my EEPROM data the servo stroke to my current servo stroke and my quadrant steps to the current quadrant steps, so amplitude and speed. And then I use EEPROM put, yeah, we already used that before, to write the whole struct to the EEPROM. And then, of course, I memorize that I already processed that change of the stroke encoder switch. And that's all. Please note, you can only save the settings when the servo is actually running. So blindly clicking on that switch button when we are not running the servo does absolutely nothing. So here's what I implemented as user interface, a very Chinese user interface for our second problem. Calibrating the 0 position and the maximum stroke of the servo. So if I stop the motion, we go into our resting position. And then if I click the stroke encoder switch, we move into the 0, into the middle position. And then I can use the stroke encoder to adjust that. And each click on the encoder is really 1 microsecond on the PWM signal to the servo. So now I'm a little bit off, and let's go back into the middle. You can probably see these little black blobs there. It's in the middle when they are disappearing. So there's the other black blob. So wee bit more. Okay, middle. And then I press the button again and it goes in the most downward position. And you see we have here, let me take some paper. We have here a little bit of wiggle room, so let's adjust that further down. Okay. Still some wiggle room. A little bit more. Now it's touching. I don't want it to touch. I'll go back a little bit. Bit too far. Yeah, that's the problem with the servo. It's not very sensitive to changes in the PWM signal. Okay, I think this is up. Okay, can I? Yeah, I can squeeze paper through. And then when I'm finished, I'm just clicking again. We go back into our resting position, and now, yeah, we can continue. And of course, that is also saved to the EEPROM. Now, sorry, big fingers. Let's have a look at the code. As you can imagine, there's a quite lot of additional code involved in that functionality, and at that point I'm not happy with the code quality. It's basically spaghetti code because we added stuff and added stuff and added stuff. But anyway, yeah, what's new here in the declarations? I have a new type, a num class calibration steps, which is just, yeah, 0, so calibrating the 0 position and calibrating the stroke max. We will use that later. All other changes happened in the loop, where I have added another Boolean, calibrating, so am I calibrating or not? And also initialize that stroke encoder switch read again to false, just, yeah, a precaution. And then I have a new static calibration step variable in which I will store the calibration step. And now I included everything we've done so far in another if statement. So if we are not calibrating, then we do our regular stuff. And if we are calibrating, we are doing something else. And we have a look at that in a second. There's also an addition here. So if we are not running and I press the stroke encoder switch, then I drive the servo to, we have seen that, to the neutral position, to the middle position, and I wait 500 milliseconds to give the servo time to do that. And then I record my stroke encoder switch and my stroke encoder position in the respective red variables, because some monkey might have turned the knob or clicked there while we were waiting half a second. Then I say I'm in calibration step 0, so calibrating the middle position, and we're going to calibrating true. And the next time we go into the loop, we are no longer in calibrating, but instead we're in this part down here, else calibrating. And here I have a switch statement, yeah, according to the calibration step which we are in. And we start with calibration step 0. And there, my first statement, I'm looking for a change in the stroke encoder position. And if there is a change, then I accordingly adjust my servo 0. Yeah, I remember the encoder position I just processed, and I write the new position out to the servo. Or if I clicked the encoder switch, I drive the servo to the servo 0 minus servo stroke max. So that was the downward position on your screen, or the most clockwise position. I wait again half a second to give the servo time. I again, yeah, record my stroke encoder switch and my stroke encoder position in the red variables, in case a monkey clicked or turned during that half second. And then I go to calibration step stroke max, and that's the next case here in the switch statement. So in calibration steps stroke max, it's analog, like above the calibration steps 0. So I look if my stroke encoder position has been changed. If it has been changed, Then I adjust now the servo stroke max accordingly. I record my servo control, my encoder position, and I write the new position, so servo 0 minus servo stroke max, so downwards to the servo. And if I'm completely finished with all that stuff and I click the encoder switch again, I write my modified variables to the EEPROM data, so the servo 0 and the servo stroke max. I write my whole EEPROM data to the EEPROM. I return to the upmost position with my servo, my normal resting position. And that's wrong because my normal resting position should be at servo stroke, not servo max. Little oversight on my behalf, because we are returning now, if we want, into the run, and the servo stroke hasn't changed. Speaking of that, I forgot something else here. Just a second. Okay, I'm sorry, but if we adjusted our servo stroke max and our current servo stroke, is greater than our new servo stroke max, then we have, of course, to limit the current servo stroke. And then I write the resting position back to the servo, so the upwards resting position. I wait 500 milliseconds for the servo to get there. And then I record my switch states in case somebody clicked in between and I don't want to process these clicks. And then I say calibrating equals false, and that's the end of the case statement. And with calibrating false, we are in our loop, now, no longer calibrating, so we go into our existing code. Okay, I don't want to leave you on that dry note, so we put that into a kinda practical application. So I have here a water bottle, half a liter, so the whole setup weighs about half a kilogram, a little over a pound. And maybe you can see it. We are currently drawing, also Servo's drawing 80-90 milliamps. If I take the load off, it goes down to 10 milliamps. And by the way, the servo arm here is 20 millimeters or 4/5 of an inch. And now let's wiggle with a maximum amplitude, but very slowly. And I'm killing here my power cables. Very nice. Let's speed things up. And I see 200 milliamps. Yeah, you cannot really see here something, can you? We can look at that. It's bigger. So sometimes 200 milliamps. But it's doing it. It's doing it. Maximum speed, 2 hertz. And I see 300, 500 milliamps. That's great. That little servo doing that. And all because we have a sinusoidal motion. Let me stop this. If we just would jerk the servo from position to position, it would not be that smooth of a motion and we would have enormous current spikes here. I think the stall current of that thing is 1.2 amps. Yeah, and we were at most at half a amp, and we are almost maxing out on the torque that that thing can deliver. Yeah, for a review of that video, card as always, link in the description. And yeah, on this a little bit more interesting practical note, I bid you farewell and say, am I in frame? I have no idea. Bye.